Hello everyone, my name is Dawid Wołosiuk, and in this presentation I'd like to show you the importance and potential of having semantically enriched building performance data, and I would like to also point out some of the challenges concerning transformation of building performance data to an ontologically structured format. This contribution is a part of an ongoing development and testing of building performance data ontology. The development was motivated by the need for a comprehensive ontological schema to represent dynamic building-related data, which should allow for a systematic building performance assessment process. The fundamental part of proposed ontology is the building performance data schema. It is based on extensive review of performance indicators and variables, and it is supposed to capture all the relevant characteristics of building performance data on a descriptive level as well as in different property domains. Ultimately, attributes included in this schema are supposed to facilitate identification and further utilization of such data in different applications. This is an overview of standard workflow of getting from a low-level performance data source to high-level application. And we identified what we think are the most relevant questions that one needs to address during this implementation process, which are directly related to this workflow. Namely, what type of data is to be semantically enriched and where does it originate from? So, performance data may originate from various heterogeneous sources and come in multiple formats. And this may greatly impact the next step of the workflow, which is data preprocessing. That brings us to the next question. Should the data be preprocessed in any way? Again, because performance data might be coming from heterogeneous sources, it might need to be preprocessed, for example, to bring the data points to a common temporal base. That would give much better utility of such data. Also, as one of the common source is performance data collected from various sensors, this data particularly should be checked in terms of quality, as it is prone to different types of errors like outliers or data gaps. This could be due to communication errors or power outages and so on. Right. The next implementation question is, how can attributes be attached to a data in an efficient manner? So, as the purpose of implementing an ontology-based schema is to give data meaning and context, which is done by providing attributes pertaining to a performance indicator or variable, collecting of these properties might become a cumbersome task, as not all of the properties, if any in some cases, might be available for scraping from a data source file or other documentation. And these attributes might have to be supplied manually, which makes this step prone to human error. We had to address all these implementation questions when testing building performance data ontology and the proposed schema. They were tested on data from multiple sensors, monitoring indoor environment and devices in an office space, but also on the data from sensors that were monitoring the outdoor environment. The semantically enriched data was stored in an HDF5 file. It is a scientific file format that is capable of storing hierarchical data structures together with attributes. And to illustrate how this ontologically structured data deposited in this file can potentially be used in performance analysis, we developed an interface between populated performance data ontology and Ladybug tools. Ladybug tools, if someone is not familiar, is a collection of environmental design applications that couple Rhino CAD software with performance simulation engines like Energy Plus or Radiance. In a testing process, a number of custom components written in Python programming language were created to enable utilization of our ontology with some of the selected Ladybug applications. In general, the created components take the selected performance variable as an input. This variable is extracted from HDF5 file based on attribute filtering, and this step you can see on this image, and process it to generate an output conforming to Ladybug's application requirement. For example, like this created component that converts solar radiation data measured via Skyscanner and pyranometers to generate an input that is required by Ladybug's radiation analysis application. Here you see this input as selected sky matrix. And the sky scanner is a device that regularly measures for a specific location the luminance and radiance of sky hemisphere, which is then represented in terms of 145 segments or patches. And here we can see this extracted sky scanner radiation data being used with Ladybug's sky dome component to visualize total annual diffuse sky radiation based on data collected in 2016. And the same output from our custom component is also used with another Ladybug's application, that is radiation analysis. This component calculates incident solar radiation on a specific surface or a group of surfaces within a selected time period. And the results are visualized directly on a 3D model that we can see here on these images. To sum up, we provided this application example to show that having a well-defined and ontologically structured data support development of universal applications and interfaces that rely on predictable input structure. And these application scenarios do not limit solely to building design, but could also support fields like building operation or building management.